Welcome to the GOA-ON webinar. We're going to get started in just a minute to give a few more participants the chance to join us. Thank you for your understanding. All right, let's get started with this. Welcome everybody to the GOA-ON webinar, and thank you for joining us today. My name is Katharina Schoh, and I'm part of the GOA-ON Secretariat, as well as an Associate Project Officer for the Ocean Acidification Projects and Programs at the Intergovernmental Oceanographic Commission of UNESCO, and I'll be moderating today's seminar. So this webinar series has 4 sponsoring organizations. We have, first of all, GOA-ON, obviously, the Global Ocean Acidification Observing Network. Secondly, NOAA, the National Oceanic and Atmospheric Administration of the US. Third, the IAEA OAICC, which stands for the International Atomic Energy Agency Ocean Acidification International Coordination Center. And last but not least, the ISC of UNESCO, which is the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. For those of you who are new to GOA-ON, we're a collaborative international network with currently over 1,100, I think, members from around about 105 countries, and designed to detect and understand the drivers of ocean acidification and the resulting impact on marine ecosystems. I'd like to give you a few housekeeping notes before we begin. During the presentation, all participants are in listen-only mode. You're welcome to type any questions during the presentation into the question box, which you can find at the bottom of the control panel on the right-hand side of your screen. We'll be monitoring all incoming questions and we'll pose them to our speaker during the Q&A session after the presentation. After the presentation, you're also welcome to use the raise your hand button to ask your question yourself. And at this time, I would like to introduce our speaker of the day, which is Professor Thomas Froehlicher. Thomas Froehlicher is a professor in climate and environmental physics at the Physics Institute of the University of Bern in Switzerland. He's interested in marine ecosystem carbon-climate interaction, with a particular focus on ocean extreme events and their impact on marine organisms and ecosystem services. Thomas studied environmental sciences at the ETH in Zurich and graduated in physics with summa cum laude at the University of Bern. He worked as a postdoctoral fellow at Princeton and as a senior researcher at ETH Zurich. During his career, Thomas has authored or co-authored well over 120 peer-reviewed publications, including work on marine heat waves and the role of the ocean in the global climate system. Thomas has co-led several Horizon 2020 research projects on a range of topics such as ocean extremes and tipping points, the global carbon cycle, and the Atlantic Ocean microbiomes. Additionally, Thomas was the lead author of Chapter 6 on extremes, abrupt changes, and managing risks, the IPCC's special report on the ocean and cryosphere in a changing climate, the SROC, and including the summary for policymakers. Thomas also contributed to the 5th and the 6th assessment report for the Working Group 1 and 2 of the IPCC, the Intergovernmental Panel on Climate Change. With all that, we're very happy to say that Thomas is here today to talk to us about compound marine heat waves and ocean acidity extremes, the drivers, trends, and impacts. And with that, Thomas, the floor is yours.
Yeah, thank you very much, Katrina, for the invitation and also for the nice introduction. I would like to share my screen now. I hope it works. Yes. Okay. So yeah, so actually I'm going to talk about the marine heat waves and also about ocean acidity extremes and their compound drivers, trends, and impacts. And yeah, this is basically work just been done by my research group, mainly Friedrich Burger, but also Jonas Ilvi, Jens Terhaar, Linus Vogt, but also by William Chung, UBC in Canada, and in collaboration also with Nikki Gruber from ETH. So I would like to start really broadly, just quickly, one slide about why we actually care about the ocean. So actually the ocean takes up about 90% of the excess heat which accumulates in the Earth system due to the increase in greenhouse gases. The ocean also takes up about 20 to 30% each year of the anthropogenic carbon we emit into the atmosphere due to the burning of fossil fuels and land use changes. And the ocean also provides food and other services to more than 3 billion people on the planet, and the vast majority actually in developing countries. So it's a really important player for regulating climate, but also for mitigating climate change. But that has usually a cost, and it actually leads to profound alterations, all these services in its physical and biochemical state. So we know that the ocean over the last 150 or 70 years has warmed up quite significantly at the surface by about 0.9 degrees, and is actually projected to continue to do so, regardless of which actually emission scenario we are actually following, either being a low emission scenario as shown here on the RCP 2.6 or a high emission scenario RCP 8.5. The uptake of anthropogenic carbon, as you probably all know, leads to a decrease in the pH, an increase in the hydrogen ion concentration. So over the last 170 years, it has decreased by about 0.1 units, and is projected to continue to do so in the future. And also due to the increasing water temperatures and the reduced ventilation of the upper ocean with the subsurface layers, we also have ocean deoxygenation. So the ocean has lost about 1 to 3% in the layers 100 to 600 meters over the last 60 years. And that is also projected to continue to do so. And we know that now for quite a long time. And we have seen these projections many times now. And actually, I guess in AR7 and CMIP7 that will be similar depending on the scenario we will actually follow. But what we have somehow realized in the last couple of years, that actually these changes are not as smooth as shown here on these time series plots. They are actually punctuated by so-called extreme events. And for heat, so that's a satellite image of the sea surface temperature. That's just one example. That's the Mediterranean Sea. You can see that in 2022, actually the sea surface temperature anomaly on that day was more than 5 degrees higher in certain parts of the Mediterranean Sea than usual. And this is often called a marine heat wave. And such marine heat waves have actually occurred over the last 2 decades in all ocean basins. So the first one we have really realized was in 2003, again in the Mediterranean Sea, where the European continent was really extremely warm. And then a little bit afterwards, also the Mediterranean Sea was actually warming up quite significantly. But we had actually marine heat waves all over the ocean. So actually in the Northwest Atlantic, there was a big marine heat wave in 2012. We had a coastal Peruvian marine heat wave in 2017. We had in the Gulf of Alaska 2016 a big heat wave, and then we had this huge blob in the Northeast Pacific. Actually, heat wave has lasted more than 1 year and actually extended quite, it actually covered quite a significant part of the Northeast Pacific. Then we also have several marine heat waves around Australia, in Western Australia, in the Coral Sea, but also in the Tasman Sea. And so that's a relatively old map, actually, and there will be a new one coming up soon. So we have a paper in Communications, Earth and Environment about a review paper on marine heat waves. And that map is actually updated there. And we included also the newest marine heat waves over the last few years on that map. So they actually occurred everywhere. Why do we care about them? And I think what really struck me when I was starting actually working on that subject was the paper in 2016 published in Science by Tom Wernberg, where they showed that this Western Australian marine heat wave here in Western Australia actually hit in end of 2011 at the west coast of Australia. And you see here the bar plots here shows actually the temperature anomalies. And in end of 2010, actually, the temperature really rose by a few degrees. And usually this ecosystem is dominated by kelp forests, which you can see here in blue. So that's the reef cover percentage of that ecosystem. And it was really just immediately or almost immediately replaced by seaweed turf. And actually all the kelp forests just died out. And since then, actually, the whole ecosystem has not really recovered since then. So it's kind of a, you could also call it an abrupt change or almost a tipping point. So even though the conditions went back to normal, that ecosystem has not really recovered. And we also actually worry about these marine heat waves because they can also affect weather over land. They can lead to heavy precipitation events, so enhanced evaporation. And then if the air actually then travels over the continent and rains out, that can lead to heavy precipitation events, but at the same time also to drought events, and at the same time also to heat waves. So it can not only affect the ecosystem in the ocean, it can also affect our weather over land. And for the carbon cycle, we just have recently done a study on what is actually the impact of marine heat waves on the air-sea carbon exchange, because we know from the terrestrial biosphere that heat waves and also drought events can significantly impact the uptake of anthropogenic carbon by the terrestrial biosphere and strongly reduce it. And we were wondering if that's actually the same in the ocean. So we have used um, the SOCAT PCO2 data set, and then actually the data sets which have extrapolated those or interpolated those data to global maps. And we have 6 different PCO2 data sets, and we analyze them. What is actually the sea air CO2 flux anomaly during marine heat waves? And that's a composite over the last 30 years since 1990. And if it's actually red, that means the marine heat wave leads to a reduction of carbon uptake. And if it's blue, it actually means it enhances a little bit the carbon uptake. So you see there's a heterogeneous pattern. So in the Eastern Equatorial Pacific, where we usually have natural carbon releasing from the ocean to the atmosphere, that release is a little bit reduced. So it leads to actually anomalous uptake of carbon during marine heat waves in that region, whereas in the mid-latitudes, low to mid-latitudes, where we usually have an uptake of carbon in these regions, that uptake is usually reduced. And if we do the global numbers, we see that actually oceanic CO2 uptake is reduced by about 8% during marine heat waves, but regionally can be up to 30%. So overall, in about 50% of the surface area of the ocean, the CO2 flux is just weakened during marine heat waves. So either if it's going out or it's going in, then the normal, the climatological sea air CO2 flux, actually that flux is usually weakened. And in about 44%, actually we cannot say with really with significance if it has changed or not during marine heat waves. And in about 8%, actually, it strengthened the uptake or the release depending on the region. So why is that? We have then looked at actually if it's actually the atmospheric CO2 in the atmosphere, or the atmospheric CO2, the ocean CO2, the solubility, or is it just the gas exchange which changes rapidly? And in most of the regions, it's actually the oceanic PCO2 which drives most of the changes in the sea air CO2 fluxes. And that's mainly in the tropics where we have usually outgassing. This outgassing is actually a bit reduced because marine heat waves lead to lower DAC, which then leads to anomalous uptake of carbon in those regions. Whereas in the low to mid latitudes, where you see here blue, it's especially the thermally induced rise in oceanic PCO2 during marine heat waves. So if you have a marine heat wave, that increases the PCO2, and that leads then to anomalous outgassing of carbon to the atmosphere. So overall, the impact is about 8% globally. Regionally can be bigger. but definitely it's not as big as, for example, during heat waves over the terrestrial over land, which has a much more significant impact on air land exchange of carbon than here what we see here in the ocean, but it can still be quite significant. Okay, so that brings me then to the outline. So what are actually marine heat waves? And what are the driving factors of them? What are the trends and attribution? And then I will actually slowly go into the biogeochemical extremes and compound events and asking the questions, have we actually overlooked the potential serious problems so far? And should we actually put more emphasis on actually understanding those compound events? Because I will show you that they have quite significant impact on marine biota, as we have seen in some case studies. Okay, so what is a marine heat wave? And that sometimes it's a bit confusing in the literature. And I think it really depends how you define a marine heat wave, what numbers you actually then get, or how they actually change. But usually IPCC just calls them a period of extreme warm near sea surface temperature that persists for days to months and can extend up to thousands of kilometers. But that doesn't really help you if you want to really put some numbers on changes, for example, or on the occurrence frequency of heat waves. So what you usually need to do is you need to define a baseline period, either fixed in time, so for example, pre-industrial or present day, or you can shift it in time so that you only look at anomalies relative to the mean background of today's conditions. Or you can also periodically update always the last 30 years and so on. And then you actually need to define the type of threshold. Usually we use a relative threshold that we can compare heat wave characteristics across the global ocean. Or for warm water corals, we usually use absolute thresholds, which are biologically informed, but they are often unknown. So actually, that's a really big knowledge gap. We often do not know the absolute threshold of some ecosystems or organisms to look at. And that's why we usually define these thresholds in a relative sense, basically just the percentile threshold. And then what type of relative threshold? Is it annually fixed? Do we only look at the warmest days per year? Or do we actually look at the anomalies throughout the year so that we can also have heat waves in winter, for example, if the temperature is just really anomalous high relative to winter conditions? And then we need to define a temporal criteria. If we can say, okay, it needs to last at least 3 to 5 days, that we call it a heat wave, or we can also apply no duration criteria. And then when we did that, we can then look at the frequency, duration, intensity, spatial extent, and the depth structure of these heat waves. And actually, recently, there was a little bit of a battle of the baselines also in the nature journals of different camps of researchers, which actually said, okay, we need to use a fixed baseline, or we need to use a shifting baseline. And I will come to that then in a minute, what I mean with that. But first, let's have a look at the characteristics of these heat waves. So they usually last a few days to more than a year, and they have a spatial scale of about 10 kilometers up to 1,000 kilometers. And then different driving processes can actually lead to SST variability at different temporal and spatial scale. We know at a short time scale and short spatial scale, air-sea heat fluxes, eddy processes, but also ocean advection and wind stress play a certain role. Then more on a longer temporal and spatial scale, Rossby waves and atmospheric blocking, jet stream and fronts, but also Kelvin waves in the ocean play a role. Then on large scale and regional climate modes play a role on even longer time scale and spatial scale. And then on really long time scales, obviously, the long-term climate change also plays a role in how it modulates the frequency of marine heat waves. So if we only look at the local scale, what drives actually those heat waves at the surface, we usually calculate a mixed layer temperature budget, which is basically we look at the temperature tendency in the mixed layer, which can then be impacted by the horizontal advection of warm or cold water, horizontal mixing by the vertical mixing, by air-sea heat flux, either being short wave, long wave, sensible or latent heat flux anomalies, or then entrainment of heat or cold water across the base of the mixed layer. We have done that in an Earth system model, and we have looked at actually what are the drivers of the onset phase of those heat waves, and what are the drivers during the decline phase of a heat wave. And here you see on the left side the climatological mean, how these components look like in the climatological mean, and then during the onset phase, it's the anomaly to the climatological mean, and during the decline phase. And what we have seen is that especially in the low to mid latitudes, it's often an anomalous air-sea heat exchange, which actually leads to anomalous SST, a warm SST, which drives those heat waves to actually grow until a peak in the SST. This is not really the case in the equatorial Pacific, where actually local mixing actually plays a bigger role of actually driving those heat waves. And then during the decline phase, it's almost reversed. Then we actually have an anomalous release of heat back to the atmosphere, which leads then to the decay of heat, of these heat waves. Obviously, so that's only the surface. I think right now subsurface processes are not really well understood. I think there we really need to actually have a better understanding to really make progress what drives subsurface heat waves. And small-scale coastal processes are often also not resolved in models, at least. And so any projections in coastal regions with these global models actually have quite large uncertainties and are really uncertain. But if we look only at the satellite data and we look at the 300 largest marine heat waves since 1982, when the satellite record started, and here is the duration of the 300 largest marine heat waves, you can clearly see that we have much more heat waves towards the end of the satellite records than at the beginning of the satellite record. And they also last longer, and also the intensity actually increased. And the blob, which was this large marine heat wave in the eastern equatorial, in the northeastern and Pacific in 2013 to 2015 actually was the longest heat wave ever recorded in the satellite period. We were then wondering actually, so what is actually the impact of global warming on those characteristics of that blob and on other heat waves? So what we did is we did an event attribution study using the probability-based approach. So we were asking, what's the probability of, for example, a blob occurring in today's climate versus the probability that the blob occurs in a counterfactual world, which is basically, in our case, the pre-industrial climate without human-caused global warming. So this counterfactual world comes from model simulations, and also the actual world comes from model simulations. And then we had the threshold from the observations, and we looked actually how many times that threshold was exceeded in today's climate and how many times in the counterfactual world. And then we calculated the fraction of attributable risk. It's basically 1 minus P0 over P1. So that means if it goes close to 1, that means human-caused global warming was the main driving factor of that heat wave to actually occur. And we looked at the intensity and the duration of the most impactful marine heat waves so far we had, and were actually reported in the literature. And just to give you one example, so this blob, the Northeast Pacific marine heat wave, had an intensity of 1.56 degrees. On average, it had a duration of almost 360 days. And when we did this attribution study, we were actually quite surprised that the intensity and such a duration was only possible due to climate change. So the blob would not have occurred based on our analysis without human-caused climate change. And all others heat waves also had a really strong component of human-caused global warming, that such an intense and long-lasting heat waves actually occurred. For example, the Northwest Atlantic marine heat wave and so on. So the question is, can we actually operationalize near real-time attribution of marine heat waves? Because we do that for land-based heat waves and other extreme events. I hope that will be done soon, or it's already done a little bit. And attribution studies of biogeochemical extremes, for example, ocean acidity extremes or impacts, are currently missing. And I think that's something we need to actually change in the near future if that's possible. If we then look at the future changes before I come to the biogeochemical extremes, so if we look at the marine heat wave changes, the probability ratio of surface marine heat waves frequency against global warming, and this is based on CMIP5 type Earth system models, and here you see the different lines are different models. So they scale the changes in the probability ratio, which is basically just how much more frequent a heat wave becomes with on the different global warming levels. These probability ratios scale very relatively well with global warming. So that means under 3-degree global warming, under, for example, RCP 8.5 scenario in the future, we will expect about a probability ratio of 40. So that means these heat waves become 40 times more frequent under 3-degree global warming that they are under pre-industrial conditions. And for a 2-degree global warming, even there, actually, the probability ratio is about between 15 and 20. So a strong increase is, we can actually expect a strong increase in these marine heat wave frequencies with global warming. And that's mainly actually in the low latitudes, especially in the tropics, where you see here that the red colors, which means a high probability ratio under 2-degree global warming. In the Southern Ocean, the probability ratio is relatively small because there the sea surface temperature is not warming up that strongly because the heat which is actually taken up is then immediately actually transported often to the lower latitudes and then subducted into the ocean interior. And the warm water is then replaced by cold water, which is upwelled in the Southern Ocean. So that's why actually the marine heat waves do not strongly increase in the Southern Ocean, but they actually strongly increase in the low latitudes and also really in the Arctic Ocean, where we have Arctic sea ice decrease, which then leads to anomalous heat uptake from the atmosphere to the ocean. That leads to a strong increase in marine heat waves. When we compare that to land-based heat waves, we have a much stronger increase of marine heat waves than land-based heat waves. Why is that? When we look at the probability distributions of surface air temperature, anomalies over land here on the left side and SST anomalies on the right side, you see that actually the distribution is much narrower for sea surface temperature than surface air temperature because the variability in the ocean temperature is much smaller than over land. So even though the ocean is actually warming up less than the land under global warming, we still get a much higher proportional increase in marine heat wave frequency than terrestrial heat waves due to this narrow SST variability compared to the variability over land. And as you have seen before, so this increase is really strong for marine heat waves, and that questions then a little bit how we define these heat waves. When we use a fixed baseline relative to pre-industrial conditions, then almost the whole ocean becomes a permanent marine heat wave. And that's why actually we had a little bit of battle in nature. So some people then suggested that we should always define an extreme event or the heat wave in that case relative to a shifting mean baseline, so relative to either present day conditions or conditions which were over the last 30 years, for example. But then there were others who actually defended that initial approach of having a fixed baseline approach. So I think overall, it's just really important when you communicate these things that you need to be clear how you define a heat wave, and you also communicate that everyone knows. So far, I always define the heat wave relative to so just an example, so for example, NOAA actually extended its alert level just in October 2023 because the sea surface temperature was so anomalous high that almost the whole map actually became saturated at the alert level 3. Or alert level 2 and 3 actually in the original product. So it's really hard then to say, okay, what's going on? So they actually extended the alert level to the alert level 4 and 5 because actually for these heat waves we also baseline then can fluctuate. So that shows you a little bit the challenge if you use a fixed baseline in time then things become saturated or a permanent heat wave. So either you actually adjust your alert levels, I think in this case, or you adjust as you get. Okay, so what are the impacts of heat waves on fish and fisheries? So we looked at that, and we looked in the northeastern Pacific in a model. What is actually the impact of these heat waves on fish biomass, on 24 different fish species? And if you see red squares, that means the fish during the heat wave, they lost biomass, they moved northward to colder waters, or they moved actually deeper. And if you see a blue square, that actually means that they actually it's the opposite. But overall, what we have seen is that marine heat waves cause changes that are at least 4 times faster and bigger in magnitude than climate change-driven decadal scale mean changes in the Pacific. So they are really important to understand how, for example, in this case, fish species respond to climate change. However, we then had an additional study just 1 year ago, led by Alexa Fredstone, where she looked at troll survey data along the North American coast, but also the European shelf systems. And she looked actually, based on that data, can we see a signature of heat waves on the biomass change observed actually in these fish species. So here you see on the y-axis the biomass log ratio, so that means if the biomass has changed from 1 year to another when we had a heat wave or not. And here on the x-axis you see the marine heat wave cumulative intensity. And what they found is, so they analyzed 250 sea bottom heat waves using more than 80,000 cells from a long-tail survey, and they actually didn't find any impact of marine heat waves on fish biomass, or at least not statistically significant. So the variations in fish biomass were so big that any marine heat wave impact was totally there would not have been detected. Or do we actually miss something fundamentally here, or are actually marine heat waves not the main drivers of fish biomass? So do we need actually to rethink the effect of marine heat waves on fish, or what is actually the role of compound events here? And that brings me to the second part of my talk. Have we actually overlooked a potential serious problem? So we actually use the fish model and then combine that with a nerve system model. And instead of looking at the hazard perspective, what happens during the marine heat wave with the fish biomass, we looked actually identified first low fish biomass because of the impact, and then we looked back what were actually the conditions which led to this low fish biomass. At least here, that's based on a model. And what we actually found is actually that low net canvas is the most important right of the really low fish biomass over more than 68% of the ocean area. And compound events are a necessary condition for extremely low fish biomass over almost 80% of the global ocean. So compound events are really crucial here to really understand the that's also for better organs and for other. And then we also say for other organs. And we actually run regional model and only look at the biophysical signature during the connect. Here we see a time period, so that's based on the one we looked at the ocean by in that area. What sort of current in that area? This is always the rare. This is the start of already where we know what this is not the first, and that means the higher.
Sorry, Thomas. I'm sorry to interrupt you. Your sound has just dropped quite a bit. Could you check your microphone, please?
Can you hear me again?
This is much better. Thank you so much.
Okay.
This is better. Yes, thank you.
Okay, so if it's gray, that means it's a triple compound extreme. So that means at the same time, high concentration, but also low oxygen concentration at the same time. What we have found is that this blob was not only a heat wave, it was also at the same time a low oxygen extreme and a high acidity extreme. Here meaning low pH extreme and not like carbon ion concentration or so. So we look specifically at hydrogen ion concentration. So maybe the impact we have seen, this strong impact during the blob, will maybe not only caused by the heat itself, it may be caused by the low oxygen and the high acidity which occurred at the same time. And that brings me to the compound events. So what are compound events? So we have a definition which has been established by Jakob Seitzer in 2018. It's a combination of multiple drivers and or hazards that contribute to societal or environmental risk. And we can actually differentiate between different compound events. So it's either preconditioned, temporarily compounding. So that means at different locations at the same time, even univariate extremes. So for example, during a El Nino period, you have morning heat waves all over in several regions actually in the global ocean. Or no, that's actually spatially compounding, I'm sorry, but the temporally compounding means you have sequence of extreme events one after the other. So first, for example, a heat wave, and then you have, for example, an acidity event, and then a low oxygen extreme, and then again a low oxygen extreme, and so on. Or you have a multivariate compound extreme, so more than one driver is outside the norm simultaneously, and that's what we are actually looking at in the next slide. So high acidity and high temperature were occurring at the same time. And we were wondering, where does that actually occur today in the global ocean? Where do these extreme events co-occur at the same time in space? And this is, you see the hotspots of compound marine heat wave and high acidity extreme. So if it's red, that means the likelihood that extreme events co-occur at the same time in space is relatively high. If it's blue, that means the probability is relatively low. And that's based on again, the TopCat PCO2 data set, and then we calculated the alkalinity based on salinity and temperature using the Liar version 2 algorithm. And then we solved the carbon chemistry, and we then make the analysis when do H plus extremes co-occur with high temperature extremes. And then you get these maps, and we compare that also to in situ station-based data, where you see here in this dot, just to make sure that our reconstruction of that map actually fits also what we see at the local scale. And it actually matches relatively well. So it's really a low likelihood in station data in the Eastern Equatorial Pacific. We also get really low likelihood values from our data we have constructed. So overall, we have a high likelihood of compound events with the positive effect of H plus from increased temperature. So during heat waves, usually H plus increases just due to the temperature effect on the carbon chemistry, which then usually outweighs the negative effect of H plus from co-occurring decrease in DAC. So I've shown you at the beginning that usually we have a decrease especially in the mid latitudes, or we have a decreased uptake of carbon, so that leads to a decrease in DAC. In the Eastern Equatorial Pacific, we have usually during heat wave, we actually have less upwelling of carbon transported to the surface. That also leads to reduced DAC. And it's always this balance between higher temperatures, higher H plus, lower DAC, lower H plus. It's the balance which driving factor wins, which then determines this basically this map here. So we also looked in the model what really drives ocean acidity extremes alone, and we actually looked at the temperature term and also at the DAC term. So it can be heat flux or carbon exchange, advection, vertical diffusion, and all other terms we actually represent in the Earth system model, and that's a study we have clustered in global biogeochemical cycles. So what we have found is, in a nutshell, that often, so heat waves are driven often by enhanced airspeed heat flux or enhanced airspeed heat flux anomaly. And in the low to mid latitudes, that's exactly the driving factors which also drives them high high acidity extremes, and that's why the likelihood is relatively high that in the low to mid latitudes, these compound extremes co-occur at the same time and space. Whereas in the low latitudes, here in the upwelling regions of the Pacific, usually you reduce the upwelling of carbon during heat waves. That's also why the likelihood is relatively low that these events co-occur at the same time. When we then look at the changes with climate change of these compound events, there are different factors which can play a role. It's either, so here you have, for example, in the x-axis temperature, on the y-axis you have H plus. How that changes, it can be just that change in the mean, which drives one variable to become more extreme, and that also then drives more compound extremes. It can be due to a change in variance, so one variable becomes more variable, and then as temporal variability increases, that leads to an increase in a compound event frequency, or the correlation actually changes across those two methods. And we've looked at that. So if we all look at the total changes in compound event frequency, that's basically this purple line with global warming levels. So high acidity extremes, they become almost permanent at the surface immediately because of the high signal to noise ratio. So every time when you have a heat wave, then you also have a compound extreme. That's strongly increases with global warming levels. But I think what's really interesting is that actually, even if you get rid of this mean change, if you define an extreme event relative to a shift in mean baseline, you still get an increase in these compounding event frequency because high acidity extremes become more frequent, even though you actually define them relative to a shift in mean baseline. And why is that? So we have looked at that, and we first looked at on which temporal scale actually the variability in H plus increases under future global warming. And we clearly see that basically the seasonal variability, which explains most of the changes in H plus variability with climate change. So that's basically at the end of the 21st century under high emission scenario. And we then also looked at the driving factors, and it's mostly just because the mean VAC level in the ocean increases, so that the seasonal variability in H plus actually increases. So even though the temperature is still the same, because the carbon content of the ocean increases, the sensitivity to the same temperature change from season to season is actually higher on the higher sea level, and that leads then to an increase in seasonality in H plus, which has been shown also by others, like more and less of the Foxy, for example, in 2018 and 11. And that then leads to this increase in compound event frequency as well. Again, coastal systems are not really well resolved in my analysis. Diurnal variability is not represented well in this post-evolution mechanics. So I would say the seasonal variability is relatively well represented. That's why we get this increase in compound event frequency, even if we account for the mean change. And then also, like actually the covariability of H plus and temperature slightly decreases with higher DAC levels in the future, and that leads to a slight decrease if we only look at that factor of compound event frequency with global warming. And that's always shown here the map for typically global warming relative to the Yes. And then if you look at other compound extreme events, so for example, compound marine heat waves and low net primary production events, they often actually occur, especially in the eastern equatorial Pacific or in the central equatorial Pacific and in the low to mid latitude. And here, the main driving factors that they actually occur in the low to mid latitude because we have lower growth because of nutrient limitation, so we have less nutrient supply to the surface ocean during marine heat waves, which reduces the growth of phytoplankton. And also the lower phytoplankton biomass actually contributes to that because phytoplankton loss, so the grazing is usually actually reduced if you have higher temperatures. So the grazing is actually increased, and then that reduces the biomass further, which will less. Yes, and then if we combine everything together, and that's a study which is now in preparation, hopefully it will be submitted soon. When we look at low oxygen extremes, which I haven't really talked a lot about, at high acidity extremes, which are the OAX extremes and marine heat waves. So at univariate, ocean acidity extremes, compound marine heat waves, ocean acidity extremes, and so on. So actually, in pre-industrial times, about 80% of the top 2,000 meters of the global oceans do not face extreme events um, every day, but 20% actually already does. And if we then look at future projections, so that's basically over the historical period, and then at 2 degrees global warming, we see that over 95% of top 2,000 meters of the ocean will actually face daily extreme or compound events under 2 degree global warming relative to a pre-industrial baseline. And even if we look at the shifting mean baseline, that also leads to a slight increase in compound event frequency from about 20% to about 30%. So even then, actually, the compound event frequency in the top 3,000 meters actually increases under 2 degree global warming relative to pre-industrial baseline. Yes, and that brings me actually to the end of my talk. So I hope I have shown you that marine heat waves strongly impact marine ecosystems, but also physical and social economic systems. So I would say it's really important to actually understand those events and what are the driving factors. Marine heat waves have doubled in frequency since the start of the satellite period and will further increase in intensity and duration when we apply a fixed baseline. And most of the impactful marine heat waves have a human-induced signal. Then when we look at compound marine heat waves, ocean acidity extremes, they occur relatively frequently in the subtropical oceans where the temperature effect dominates the DAC effect, but they are relatively rare in the equatorial Pacific and in the mid to high latitudes. And the blob in 2013 to 15 was a compound event, a triple compound event, and also compound event frequency will strongly increase under global warming. And there are at the moment conflicting findings on the impact of marine heat waves on fish, but I think compound events, specifically marine heat waves, low net primary production events, might have a greater effect than previously thought on low fish biomass. And maybe also marine heat waves and high acidity events may have maybe a synergistic effects also on calcifying organisms and a stronger impact on calcifying organisms than we have previously thought. Yeah, that's it from my side. And thank you very much for your attention. And I'm happy to take questions. Thank you.
Thank you very much for this very thorough webinar. Presentation was amazing. I have learned a lot today, and I hope so has our audience. If you are feeling a little shy, you can type in your questions into the Q&A box, or otherwise I would encourage you to raise your hand to ask your question directly. I actually have a question. Do you feel that we understand these compound events and these extreme events, or do you feel that there are data gaps that we need to fill in order to improve our understanding and our prediction capabilities?
Yeah, that's a really good question. I actually feel that we do not really understand them very well because that's also one reason why I only showed the surface layers and compound events in the surface layers, because there we have most of the data, but even there the PCO2 data set is really sparse. And we often lack, for example, in the Southern Ocean, wintertime data, so we cannot really say with high confidence what's going on in these remote areas. And if we then go below the surface, and we know from model studies that actually below the surface, high acidity extremes are more intense, and even they last longer, at least in the models, but it's really hard to constrain the models because we do not really have enough data to constrain them. And then if it comes to compound events, which are even more rare than these univariate extremes, it's even more difficult. And so we actually need not only, I mean, we often lack actually we do not really know well the climatological mean state of certain variables, but to look at extreme events, we also need long time series to actually look at these rare events. So I think, yeah, it would be really beneficial to sustain the existing observational networks, but also to extend them to actually really, that we can look at these compound extreme events in more detail, yes.
Thank you for that. I agree. I think long-term data is something that is just really going to help us understand better. And unfortunately, lots of these are being discontinued. We have a question from our audience, which is, what is the general depth range of marine heat waves?
Yeah, that's a good question. Actually, that depends on the region. So often they are basically in the mixed layer, but they can also go below the mixed layer. And they can even actually detach from the surface. So they can actually also occur at subsurface. So if you have water masses which actually move back and forth at subsurface, then actually they can actually lead to a heat wave at subsurface without actually detecting them from satellites, for example. So it's a bit, often they are connected, but there are also actually, sometimes they're also disconnected. And I think just yesterday there was a paper published in Nature, which actually shows that many actually these small scale heat waves in the subsurface are often actually detached from the surface and cannot be detected from the surface. So yeah, so if we look at subsurface impacts of, or most of the ecosystems and organisms actually live at subsurface and not really at the surface, at the skin layers where we actually have the satellite data. So there, yeah, so we really need more data there, and these heat waves can actually usually last longer actually at subsurface than at the surface, where at the surface, sea surface variability is often impacted by atmospheric noise, and then it can lead to really short heat waves, whereas at subsurface, that's not really the case, and they usually last longer, yes.
So there's hidden subsurface heat events. That's just scary.
Yes, so yeah,
Um,
they can be, yes.
that sounds, would something like ergo floats or something similar be able to detect those or help detect those?
Yes, definitely. So if Argo flow goes through such a heat wave, and if it goes up or down, yes, it definitely can. And also, there are relatively good reanalysis data sets now available. So, for example, for this fish study where we looked at so these troll survey data, they are actually taken at the bottom of the ocean. Some of them actually, and so we used actually reanalysis data, the Glorious reanalysis data set, which has a relatively high resolution and is actually relatively good in coastal regions. So we can actually use those data sets, at least for temperature, to actually say something about subsurface marine heat waves. But when it comes to biogeochemical data, then it's even more difficult, yes.
Mm, very true. We have a question again in the box. Do you think the marine carbon dioxide remove, the MCDR, using alkalinity enhancement will work with marine heat waves becoming more frequent, or will that impede the success?
That's a really good question. I mean, what we see is the heat waves, they usually reduce the uptake of carbon by the ocean by about 8% globally, locally up to 30%. So ocean alkalinity enhancement may actually increase then the uptake, but that also then may comes at the cost of subsurface higher acidity, which then would probably lead to more compound events at subsurface. But that's, yeah, it's a really good question. So I think people are now thinking about that, if we can somehow, yeah, if actually these techniques would actually work in extreme environment like a heat wave. But I haven't really seen any studies which have really looked at that in much more detail and which I think is really robust yet. So, but that's a really good question. So I think we need to understand that properly before we actually deploy any of those CDR techniques, or actually even before they are actually considered. Actually, we need to understand those first. Yes.
Yes, I think we currently don't understand enough about how they function in their
Mhm.
current environment, let alone any predicted new extremes. Very good. Thank you so much for the question and for your
Mhm.
answer. Are there any more questions from the audience? You can also raise your hand and ask your question directly. We can unmute you. Right. I have another question.
Mhm.
Um, if you were to prioritize parameters for observations that we would need, do you have a wish list of what we need to observe in order to better understand these extreme events?
Yeah, it's a good question. I mean, subsurface temperature data would really be many things
Mm-hmm.
because that's then determining the physics, which also impacts the biogeochemistry. But overall, I think PCO2 at subsurface would already be, or just the carbon content would be really useful on higher temporal resolution. I think it depends a little bit what you are interested in. I think for higher trophic organisms, also oxygen is really important, and we do not really have a lot of oxygen data. Well, we have, but not, I would say not enough. So I would say, yeah, I mean, yeah, subsurface temperature data for me would be already really good to have them more frequently and spatially also better resolved. And especially also just the PCO2 data set, or the PCO2 measurements. I mean, over the last few years, the amount of measurements which have been taken, as far as I understood, has decreased over time a bit. And that should not be the case if we want to understand, especially also when it comes to the older discussion of CDR and so on. If we do not really know the baseline very well, how can we then say something about if we want to perturb something, how the things will change? So I think we need to break this trend and really increase the data coverage of the PCO2 at the surface, but also, the carbon content at subsurface. Yes.
Excellent. Obviously, this is a very personal question because depending on your research interest, it is going to be different. I'm thrilled to hear that you also agree on PCO2 measurements and subsurface being very important. We're obviously investigating a lot of ocean acidification
Hmm.
in GOA-ON, and so yes, we see severe lack of data in great many regions, which obviously impedes any global stock take of what is actually happening. So I think this is a very good end to this fascinating webinar. I would like to thank you all for attending and particularly like to thank our speaker. This has been amazing. We will be back with our webinars in the future, so please keep an eye on the GOA-ON social media and the newsletters. And I would also like to remind you that we're kicking off OA week again. This is the fourth time we're doing this. So Monday, 18th of November to Friday, 22nd of November, we will have a full program of ocean acidification related talks and discussions for you. And with that, I thank you very much. Thank you again, Dr. Professor Froehlicher, and enjoy the rest of your day, everybody. Goodbye. See you next time.